until the 1970s, if you wanted to exchange private information with someone, you would first have to meet up in person and share a secret key. This same key would be used to encrypt and decrypt messages, so it's known as a symmetric key algorithm. As long as no one else gets their hands on the key, your messages are safe. But now, what if you want to send information to someone you've never met, and it's too hard to arrange an in-person meeting? You can't share a key over an unsecure channel like a phone line or the mail because it could be intercepted. And this is what in 1977 led three scientists, Revest, Shamir, and Adelman, to come up with an encryption breakthrough. Today it's known by their initials RSA, and it works something like this. Every person has two really big prime numbers, all their own, which they keep secret. They multiply these numbers together to get an even bigger number, which they make public for everyone to see. Now, if I want to send someone a private message, I use their big public number to garble my message, and I garble it in such a way that it is impossible to ungarble without knowing the two prime factors that made that number. This is an asymmetric key system since different keys are used to encrypt and decrypt the message. So it's easy for my intended recipient to decode, but impossible for everyone else unless they can factor that large public number. Now, someone could try to factor it using a supercomputer in the best-known factoring algorithm, the general number field sieve, but modern cryptography uses prime numbers that are around 313 digits long. Factoring a product of two primes this big, even with a supercomputer, would take around 16 million years. But not on a quantum computer. See, in normal computers, a bit can only be in one state at a time, either a 0 or a 1. So if you had 2 bits, they could be in one of 4 possible states, 0, 0, 0, 1, 1, 0, or 1, 1. Let's say each of these states represents a number, 0, 1, 2, or 3. If we want to do a calculation, for example, raising 7 to the power of one of these numbers, we can only do it for one state at a time. In this case, 7 squared, and so we get the answer 49. Quantum computers consist of qubits, which also have 2 states, 0 or 1. But unlike a classical bit, a qubit doesn't have to be in just one state at a time. It can be in an arbitrary combination of those states, a superposition, if you will, of 0 and 1. So if you have 2 qubits, they can exist simultaneously in a superposition of 0, 1, 2, and 3. Now, when we repeat the same calculation, it will actually perform the calculation for all of those numbers at the same time. And what we're left with is a superposition of the different answers, 1, 7, 49, and 343. If we add another qubit, we double the number of possible states. So with 3 qubits, we can represent 8 states, and thus perform 8 calculations all at once. Increase that number to just 20 qubits, and you can already represent over 1 million different states, meaning you can simultaneously compute over 1 million different answers. With 300 qubits, you can represent more states than there are particles in the observable universe. This sounds incredibly powerful, and it is, but there is one very big catch. All of the answers to the computation are embedded in a superposition of states. But you can't simply read out this superposition. When you make a measurement, you only get a single value from the superposition, basically at random, and all the other information is lost. So in order to harness the power of a quantum computer, you need a smart way to convert a superposition of states into one that contains only the information you want. This is an incredibly difficult task, which is why for most applications, quantum computers are useless. So far, we've only identified a few problems where we can actually do this. But as luck would have it, these are precisely the problems that form the foundation of nearly all the public key cryptography we use today.